NASA's James Webb Space Telescope has achieved a groundbreaking feat by capturing the first real image of the enigmatic interstellar object 3Y Atlas. This remarkable milestone opens a new chapter in our understanding of cosmic wanderers and the mysteries they hold. The data reveals unprecedented details that challenge previous notions about interstellar visitors. Join us as we unravel the story behind the flicker in the telescope's data leading to this profound discovery, the object's incredible speed from the void, and the secrets it may unlock about our universe. The flicker in the data. In late 2025, astronomers noticed a faint flicker within vast datasets collected by advanced telescopes across multiple observatories worldwide. Initially dismissed as background noise or instrumental error, this subtle signal sparked curiosity among researchers at NASA when artificial intelligence algorithms began flagging anomalous patterns. Analysts utilized cutting-edge machine learning algorithms to isolate these anomalous data points corresponding to an object moving at extraordinary speed through our galaxy. Subsequent observations confirmed the flicker as 3Y Atlas, a massive interstellar visitor entering our solar system from the depths of space. This serendipitous detection was a testament to the increasingly sophisticated analytical methods enabling the discovery of elusive cosmic travelers from the vast interstellar void. The discovery process highlighted how modern astronomy relies on both advanced technology and human intuition to identify phenomena that would have been completely invisible to previous generations of scientists. The flicker represented humanity's first glimpse of what would become the most significant interstellar discovery since Oumuamua, offering unprecedented insights into phenomena previously beyond our reach and understanding. 152,000 miles per hour from the void. 3Y Atlas barrels through space at a staggering velocity of approximately 152,000 miles per hour, or about 68 kilometers per second, defying all known celestial norms and expectations for objects in our cosmic neighborhood. This extraordinary speed has been confirmed through precise orbital tracking conducted by teams at NASA's Jet Propulsion Laboratory, utilizing multiple ground-based and space-based observation platforms. The velocity calculations show this speed dwarfs any traditional simulation of interstellar objects passing through our solar system, suggesting origins from an incredibly distant star system. Such immense velocity indicates the object has traversed the vast interstellar void for potentially millions of years, subjected to cosmic radiation bombardment and gravitational perturbations from countless stellar encounters. Its trajectory through the ecliptic plane positions it for brief but critical visibility windows, prompting astronomers worldwide to mobilize for intensive observation campaigns using every available telescope and sensor array. Understanding this rapid journey through space enhances our fundamental grasp of galactic dynamics and the frequency of alien visitors crossing our cosmic neighborhood, while raising profound questions about the forces that could accelerate such massive objects to these incredible speeds. 3 visitors, 7 years. Since the epical discovery of Oumuamua in 2017, followed by the comet-like 2I Borisov in 2019, humanity has witnessed 3 confirmed interstellar intruders within a span of just 8 years. This unprecedented sequence has fundamentally transformed our perception of the solar system's place within the broader galactic environment and the frequency of cosmic visitors. Each visitor displays unique physical and dynamic attributes, painting an increasingly complex picture of materials ejected from diverse planetary systems across the galaxy. The arrival of 3I Atlas, significantly larger and faster than its predecessors, magnifies the urgency in understanding the true diversity and origin of such objects in our cosmic neighborhood. As observational technology advances and detection methods become more sophisticated, the frequency of such encounters may reveal long-hidden cosmic realities about interstellar traffic patterns. The pattern suggests that interstellar visitors may be far more common than previously imagined, fundamentally challenging our understanding of solar system dynamics and the movement of matter between star systems. These discoveries collectively indicate that our solar system exists within a much more active and dynamic galactic environment than scientists previously recognized, with implications for planetary formation, asteroid populations, and the potential for life-bearing materials to travel between worlds. James Webb's metallic discovery. So James Webb's metallic discovery, well, the James Webb Space Telescope's recent high-resolution imaging of 3I/Atlas, has delivered completely unexpected revelations about its surface properties and composition. And honestly, these findings have just stunned the scientific community. Comprehensive spectral analysis, which was conducted by Dr. Liam Cheng and his international research team, detected a predominantly metallic composition. This fundamentally challenges those long-held assumptions that interstellar objects are mostly icy or rocky bodies. Now, this distinctive metallic signature, it suggests either advanced natural processing through some truly extreme cosmic conditions, or, potentially, artificial construction by unknown technological means. Reflected light patterns captured by Webb's advanced infrared instruments indicate an unusually smooth, potentially engineered surface, instead of the rough, pitted texture that's typical of natural asteroids or comets. The metallic composition even appears to include elements not commonly found in typical solar system objects, like rare earth metals and isotopes that suggest formation under, well, exotic stellar conditions. These groundbreaking findings open the door to revolutionary hypotheses regarding non-natural origins, and they're really compelling scientists worldwide to expand their investigative methodologies and fundamentally reconsider their definitions of cosmic phenomena. The discovery has prompted emergency funding for additional observation time, and it's sparked some intense international collaboration to analyze every detail of this unprecedented visitor before it disappears forever into the depths of space. The machine that steers itself. This is honestly one of the most astonishing and scientifically challenging aspects of 3I/Atlas. It's the object's apparent ability to modify its trajectory mid-course, which strongly implies the presence of an intrinsic navigation or guidance system. Groundbreaking research led by aerospace engineer Dr. Sofia Martinez has documented subtle but measurable variations in velocity and orientation that just remain completely inconsistent with gravitational influences alone. These adaptive steering capabilities suggest highly sophisticated onboard systems, either responding intelligently to external stimuli or fulfilling some form of pre-programmed interstellar mission. This phenomenon, well, it raises some profound and honestly unsettling questions about whether such objects represent autonomous probes, rather than just mere geological debris drifting through space. The trajectory adjustments seem to occur at specific intervals and follow patterns that suggest deliberate course corrections, probably designed to optimize the object's path through our solar system. Such capabilities would require technology far beyond anything currently possessed by human civilization, involving either advanced artificial intelligence or direct control by some form of intelligence. The implications here challenge existing space exploration frameworks, and they invite some pretty serious speculation about extraterrestrial engineering and the possibility that 3I/Atlas represents humanity's first encounter with genuine alien technology actively operating within our solar system. Information blackout. Despite intense scientific scrutiny from observatories worldwide, much crucial information about 3I/Atlas still remains, well, mysteriously enigmatic due to unprecedented government-imposed data restrictions and communication blackouts. Classified satellite data and systematic communications jamming really hint at a broader, coordinated information suppression campaign designed to deliberately suppress sensitive knowledge regarding the object's true nature and potential origins. Whistleblowers, including former intelligence officer Dr. Eleanor Hayes, suggest that agencies across multiple governments participate in coordinated secrecy operations that span international boundaries. This systematic information blackout has fueled widespread conspiracy theories and public frustration, while at the same time underscoring the immense challenges legitimate scientists face in accessing comprehensive datasets needed for proper analysis. The restrictions appear to target specific wavelengths of electromagnetic observation and particular types of gravitational measurements, which suggests authorities know exactly what they want to conceal from public knowledge. Transparency advocates and scientific organizations worldwide argue vigorously for immediate declassification to advance scientific understanding and, properly prepare humanity for potential first contact scenarios. The secrecy has created an unprecedented divide between official government statements and the growing body of leaked evidence, suggesting 3I/Atlas represents something far more significant than a simple interstellar asteroid. Adaptive shielding technology. So, recent theoretical models developed by leading physicists propose that 3I/Atlas employs this, highly advanced adaptive shielding technology. It's apparently capable of rendering it nearly invisible to conventional detection methods, and that's across multiple electromagnetic spectra. The Max Planck Institute, they've elaborated on these sophisticated hypotheses involving electromagnetic cloaking fields and dynamic surface morphing, which could help explain the object's, mysteriously elusive signatures. Such revolutionary shielding technology would, at least in theory, allow the object to systematically evade host planetary defense systems and observational arrays, basically making completely discrete movement through solar systems possible. The proposed technology involves real-time manipulation of electromagnetic properties, possibly through programmable metamaterials that can alter their reflective and absorptive characteristics instantaneously. Investigations into these extraordinary properties may, honestly, revolutionize human understanding of stealth technology, with some pretty profound implications for both planetary defense systems and future space exploration capabilities. The adaptive shielding seems to actually respond to different types of observation attempts, becoming more transparent to certain wavelengths while staying opaque to others, in patterns that, suggest intelligent control. If confirmed, this technology would represent a quantum leap in material science and electromagnetic manipulation, far beyond anything achievable with current human knowledge, and could potentially provide blueprints for revolutionary advances in spacecraft design and planetary protection systems. The Ancient Probe Network. So, emerging evidence increasingly suggests that 3I/Atlas might represent a crucial component of a vast ancient probe network, potentially constituting a galactic surveillance system initiated by an advanced civilization that predates human existence by millions of years. Leading astrobiologist Dr. Maya Singh describes how such interconnected probes could, in theory, monitor planetary systems across thousands of light years, relaying comprehensive information through quantum entanglement communication systems or, even faster than light transmission methods. These sophisticated networks might encode prime number sequences within their thermal signatures, functioning as distinguishing identification markers or complex mathematical messages designed for detection by emerging technological civilizations. The probe network theory, honestly, suggests a level of galactic organization and long-term planning that completely transcends human technological capabilities and temporal perspectives. Each probe would operate semi-autonomously while maintaining connection to a larger intelligence network, gathering data on planetary development, biological evolution, and technological advancement across, countless worlds. Such a discovery would fundamentally redefine humanity's place in the cosmos, indicating we exist within a much larger, interconnected interstellar intelligence system that has been operating for eons. The implications extend really beyond mere scientific curiosity, suggesting that human development may have been observed and possibly influenced by these ancient sentinels, heralding a new era in astronomical, philosophical, and existential understanding of our role in the universe. Prime numbers in heat signatures. Scientists analyzing the thermal emissions from 3I/Atlas have detected increasingly intriguing patterns featuring prime number sequences, which, many researchers interpret as deliberate mathematical signals rather than just random electromagnetic noise. A renowned mathematician emphasizes that these precise numerological features could represent a sophisticated intelligent encoding method, strongly indicating deliberate communicative intent from the object. These remarkable findings add substantial credence to the hypothesis that 3I/Atlas represents an artificial probe, and they've sparked unprecedented new interdisciplinary studies combining advanced astrophysics with information theory and cryptographic analysis. The presence of prime number sequences in electromagnetic emissions is widely considered among scientists as, honestly, potentially universal evidence of technological civilization, effectively bridging the gap between purely cosmic phenomena and potential extraterrestrial intelligence communications. The patterns appear in multiple frequency ranges and follow mathematical progressions that would be, virtually impossible to produce through natural processes alone. The sequences begin with simple primes like 2, 3, 5, and 7, then progress to increasingly complex mathematical relationships that suggest a deliberately constructed communication protocol. International teams of mathematicians and physicists are working around the clock to decode additional layers of meaning embedded within these thermal signatures, while astronomers continue monitoring for any changes in the transmission patterns that might indicate active communication attempts or responses to human observation efforts. We were never the observers. The revolutionary notion that humanity has never been the sole observers of the cosmos is, honestly, gaining unprecedented traction through intensive study of 3I/Atlas and its profound implications for our understanding of galactic civilization. Ongoing research strongly suggests that Earth has been an integral part of a carefully monitored network within a complex universe where multiple advanced civilizations may observe and interact discreetly across vast interstellar distances. A philosopher promotes the groundbreaking idea that 3I/Atlas may represent a sophisticated sentinel, serving as a stark reminder that our species has been under systematic scrutiny by significantly more advanced intelligences throughout our evolutionary development. This paradigm-shifting revelation fundamentally challenges deeply ingrained anthropocentric worldviews and invites, profound reflection on the true nature of consciousness, intelligence, and existence within a potentially vast, collaborative galactic community. The evidence suggests that what we interpreted as humanity's journey of discovery and exploration has actually been occurring under the watchful eyes of ancient observers who have been cataloging our progress for millennia. This realization transforms our entire perspective on human achievement, technological development, and our future role in what appears to be a much more interconnected and sophisticated cosmic civilization than we ever dared imagine, fundamentally altering our approach to space exploration, scientific research, and our search for extraterrestrial intelligence. James Webb's capture of 3I/Atlas's first real image marks a historic milestone in humanity's encounter with the cosmos and our understanding of our place within it. The implications resonate across science, philosophy, and society, hinting that we may be standing on the threshold of profound discovery and possible first contact with extraterrestrial intelligence. What are your thoughts on these revelations? Share your perspectives in the comments. Subscribe to CI and Y for more cosmic insights and continue looking upward to the stars where ancient mysteries await our discovery. When CERN's Large Hadron Collider smashed protons together at unprecedented energies, scientists weren't just hunting for new particles. They were searching for something far more extraordinary: microscopic black holes. These quantum-scale phenomena, predicted by cutting-edge theories involving extra dimensions, could revolutionize our understanding of gravity and space-time itself. Today on Sci and Y, we're unveiling what really happened when the world's most powerful particle accelerator went hunting for the universe's most mysterious objects. The quest for quantum black holes. CERN's scientists embarked on one of the most ambitious experiments in physics history, deliberately trying to create black holes in a laboratory setting. The search for microscopic black holes at CERN represents a fascinating intersection of theoretical physics and experimental reality. Unlike the massive black holes found in space, these quantum black holes would be incredibly tiny, existing at subatomic scales and lasting for mere fractions of a second. The CMS experiment at CERN's Large Hadron Collider has been actively searching for these phenomena since the facility's early operations. According to CERN's official documentation, some theoretical models suggest that microscopic black holes could form when particles collide with sufficient energy, particularly if our universe contains extra spatial dimensions beyond the familiar three. These theories, including the Arkani-Hamed-Dimopoulos-Dvali model and the Randall-Sundrum scenario, propose that gravity might be much stronger at quantum scales than previously thought. The LHC's proton-proton collisions at energies up to 13 TeV create conditions where, according to these models, space-time itself could briefly collapse into microscopic black holes. If formed, these quantum objects would immediately evaporate through Hawking radiation, producing distinctive particle signatures that CERN's sophisticated detectors could potentially observe. The theoretical foundation. The possibility of creating black holes in particle accelerators stems from revolutionary theories that suggest our universe has hidden dimensions we can't perceive. The theoretical framework for microscopic black hole production relies on models involving extraspatial dimensions. In standard four-dimensional physics, creating a black hole would require concentrating energy equivalent to about 10 to the 19th GeV, far beyond any human-made technology. However, Theories like the ADD model propose that gravity might propagate through additional dimensions, while other forces remain confined to our familiar three-dimensional space. This would effectively lower the energy threshold for black hole formation to potentially just a few TeV, precisely within the LHC's operational range. Dr. Lisa Randall and Raman Sundram developed influential models suggesting that if extra dimensions exist, the fundamental scale of gravity could be much lower than previously thought. These theories emerged to solve the hierarchy problem, explaining why gravity appears so much weaker than other fundamental forces. If correct, when protons collide at nearly light speed in the LHC, they could concentrate enough energy within a tiny region to exceed the Schwarzschild radius, causing spacetime to collapse into a microscopic black hole. The mathematics behind these theories is elegant but complex, requiring sophisticated computational models to predict observable signatures. CERN's experimental search. Armed with the world's most sensitive particle detectors, CERN scientists began their systematic hunt for evidence of microscopic black hole creation. The CMS experiment at CERN has conducted extensive searches for microscopic black hole signatures in high-energy proton-proton collisions. Using data collected during the LHC's operations at 7 TeV center of mass energy, researchers analyzed collision events looking for the distinctive particle sprays that would result from black hole evaporation. According to CERN's published results, if microscopic black holes were produced, they would evaporate almost instantaneously through Hawking radiation, creating characteristic patterns of subatomic particles detectable by the CMS detector surrounding the collision point. The search methodology involved examining invariant mass spectra of particle jets, looking for anomalies that couldn't be explained by standard particle physics. Scientists used sophisticated Monte Carlo simulations to model expected black hole signatures, comparing these predictions against actual collision data. The ATLAS experiment has also conducted similar searches, analyzing electron plus jet and muon plus jet invariant mass spectra with 140 inverse femtobarns of collected data. These experiments represent some of the most sensitive searches ever conducted for quantum gravitational effects, pushing the boundaries of what's experimentally accessible in fundamental physics. The surprising results. After analyzing millions of particle collisions, CERN's results challenged expectations and honestly, revealed something unexpected about the nature of reality. The experimental searches conducted by both the CMS and ATLAS experiments have yielded some pretty fascinating results. No direct evidence for microscopic black hole production has been found in the energy ranges examined so far. The CMS experiment's analysis of 7 tera-electron-volt collisions ruled out the existence of microscopic black holes, up to masses of 3.5 to 4.5 tera-electron-volts, for various theoretical models. More recently, the ATLAS experiment search using 13 tera-electron-volt collision data set even more stringent limits, excluding quantum black hole production up to 9.2 tera-electron-volts in the Arkani-Hamed-Dimopoulos-Dvali model, and 6.8 tera-electron-volts in the Randall-Sundram model. These non-observations are actually scientifically significant because they constrain the parameters of extra-dimensional theories. The absence of black hole signatures at these energy scales suggests that either extra dimensions don't exist as these models predict, or the fundamental scale of gravity is higher than theorized. However, these results don't definitively rule out microscopic black holes. They simply push the energy threshold higher, potentially requiring future collider experiments with even greater energies to test these theories conclusively. Safety considerations and public concerns. The prospect of creating black holes on Earth sparked widespread public concern, forcing scientists to address some pretty fundamental questions about experimental safety. Public fears about CERN creating dangerous black holes have persisted since the LHC's inception, and honestly, they've been amplified by popular culture and social media speculation. CERN has consistently addressed these concerns through comprehensive safety assessments and public education. According to CERN's official safety documentation, any microscopic black holes produced would be perfectly safe because they would evaporate almost instantaneously through Hawking radiation. The fundamental safety argument relies on cosmic ray interactions. High-energy particles from space constantly bombard Earth's atmosphere with energies far exceeding the LHC's capabilities, up to 10 to the 20th electron volts. If dangerous black holes could be produced at LHC energies, cosmic rays would have already created them throughout Earth's 4.5 billion-year history. Dr. John Ellis and other CERN physicists have emphasized that even hypothetically stable microscopic black holes would be harmless because they would interact so weakly with ordinary matter that they would pass through Earth without effect. The LHC Safety Assessment Group concluded that the experiments pose no conceivable danger, with multiple independent reviews confirming these findings. Hawking radiation and quantum effects. Stephen Hawking's groundbreaking theory predicts that microscopic black holes wouldn't grow and consume matter. Instead, they would explode in bursts of quantum radiation. Hawking radiation theory, developed by Stephen Hawking in the 1970s, fundamentally changed our understanding of black hole behavior. According to this theory, black holes aren't completely black but emit radiation through quantum effects at their event horizons. For microscopic black holes, this process would be extraordinarily rapid. Objects with masses comparable to elementary particles would evaporate in approximately 10 to the minus 27 seconds. The smaller the black hole, the more intense its Hawking radiation and the faster it evaporates. This creates a natural safety mechanism. Any microscopic black holes produced at CERN would immediately decay into standard model particles before they could interact with surrounding matter. The evaporation process would produce a distinctive spray of particles including photons, electrons, muons and quarks, creating detectable signatures in CERN's instruments. Theoretical calculations suggest that the temperature of Hawking radiation from a microscopic black hole would be incredibly high, potentially reaching 10 to the 17th Kelvin. This extreme temperature would cause the black hole to radiate away its entire mass almost instantaneously, making it impossible for such objects to grow or pose any danger to their surroundings. Implications for extra dimensions. The search for microscopic black holes at CERN represents honestly humanity's first experimental probe into the possibility that our universe contains hidden spatial dimensions. The theoretical models predicting microscopic black hole production are, intimately connected to theories of extra dimensions. These models suggest that our familiar three-dimensional space might actually be embedded in a higher dimensional reality, with gravity able to propagate through these additional dimensions, while other forces remain confined to our observable space. The ADD model, which was developed by Nima Arkani Hamed, Savas Dimopoulos, and Gia Dvali, proposes that gravity appears weak because it spreads out through large extra dimensions. Meanwhile, the Randall-Sundrum model suggests that we live on a three-dimensional brain within a five-dimensional space, with gravity concentrated near our brain by the geometry of space-time itself. CERN's experimental limits on black hole production provide, crucial constraints on these theories. The absence of black hole signatures at current energy scales suggests that if extra dimensions exist, they must be smaller or configured differently than some models predict. These results represent the first experimental tests of quantum gravity theories, providing invaluable data for theoretical physicists working to understand the fundamental structure of spacetime and the unification of quantum mechanics with general relativity. Advanced detection methods. CERN's scientists, have developed some truly revolutionary detection techniques to identify the fleeting signatures of microscopic black holes among millions of particle collisions. The search for these tiny black holes required developing really sophisticated analysis techniques to distinguish potential black hole signatures from ordinary particle physics processes. The CMS and ATLAS detectors use these multi-layered systems, silicon trackers, electromagnetic calorimeters, and muon chambers, to reconstruct particle trajectories and energies with, honestly, extraordinary precision. Scientists have also developed specialized algorithms to identify the high multiplicity particle jets that would result from black hole evaporation, looking for events with unusually large numbers of particles produced in spherically symmetric patterns. On top of that, machine learning techniques have been employed to analyze vast datasets, training neural networks to recognize potential black hole signatures among the billions of collision events recorded. The analysis focuses on invariant mass distributions, searching for resonances or anomalies that just can't be explained by standard model processes. Researchers use Monte Carlo simulations, which incorporate various black hole models, to predict expected signatures, then compare these predictions against real data using statistical methods. The detection challenge is immense. Potential black hole events would be extremely rare, requiring analysis of petabytes of collision data to identify possible candidates among overwhelming backgrounds of ordinary particle interactions. future prospects, and higher energies. As CERN prepares for even more powerful experiments, the search for microscopic black holes is, well, entering a new phase with unprecedented energy scales. The high-luminosity LHC upgrade, which is scheduled for completion in the late 2020s, will actually increase collision rates by a factor of 10, providing vastly more data for rare event searches. This enhanced capability could push the search for microscopic black holes to higher mass scales, potentially reaching the thresholds predicted by some extra-dimensional models. Looking ahead, future collider projects, including the proposed future circular collider, with energies up to 100 TeV, would provide even more sensitive probes of quantum gravity effects. The increased energy and luminosity would allow scientists to explore black hole production at mass scales up to 50 TeV or higher, definitively testing many theoretical predictions. Advanced detector technologies under development like improved calorimetry and faster data acquisition systems will enhance the sensitivity to black hole signatures. Theoretical work is also continuing to refine predictions, with new models suggesting alternative signatures that might be more easily detectable. Really, the combination of higher energies, improved detectors, and more sophisticated analysis techniques may finally provide the experimental breakthrough needed to either discover microscopic black holes or definitively rule out their production at collider energies. The broader impact on physics. Whether CERN finds microscopic black holes or not, the search itself is, honestly, revolutionizing our understanding of fundamental physics and the nature of reality. The quest for microscopic black holes at CERN represents more than just hunting for exotic objects. It's really testing the very foundations of our understanding of space-time, gravity, and quantum mechanics. The experimental limits already established have constrained theories of extra dimensions and quantum gravity, forcing theorists to refine their models and develop new approaches to unifying fundamental forces. The sophisticated detection methods developed for black hole searches have advanced experimental techniques across particle physics, improving our ability to discover other new phenomena. The safety analyses conducted for these experiments have also deepened our understanding of cosmic ray interactions and astrophysical processes. Even negative results provide valuable scientific information, ruling out certain theoretical possibilities and guiding future research directions. The interdisciplinary nature of this research has fostered collaboration between particle physicists, cosmologists, and theoretical physicists, leading to new insights about the universe's structure. As CERN continues pushing the boundaries of experimental physics, the search for microscopic black holes remains a powerful probe of reality's deepest mysteries, potentially revealing whether our universe truly contains hidden dimensions and whether quantum mechanics and gravity can be unified into a single theoretical framework. CERN's search for microscopic black holes represents humanity's boldest attempt to probe the fundamental nature of reality itself. While no black holes have been detected yet, the journey has revolutionized our understanding of physics and pushed the boundaries of what's experimentally possible. If you're fascinated by these cutting-edge discoveries and want to explore more mind-bending physics mysteries, hit that like button, share your thoughts in the comments, and subscribe to Sci and Y for more journeys into the universe's deepest secrets. Thanks for watching. Keep questioning reality. What if the third interstellar visitor ever discovered was not a comet, but a billion-year-old alien messenger? In the summer of 2025, a faint object designated 3I Atlas streaked into our solar system, and a controversial hypothesis immediately captured the world's attention. This was no ordinary rock. The idea of advanced alien technology made global headlines, but NASA quickly stepped in with a powerful, evidence-based response that settled the debate. So what did they find? Let's explore this together. The Atlas discovery in Chile. So, where does a story like this begin? It starts with our ever-watchful eyes on the sky. The story began on July 1, 2025, when the Asteroid Terrestrial Impact Last Alert System, or ATLAS, a robotic survey telescope at the El Sos Observatory in Chile, detected a faint object with an initial apparent magnitude of plus 19.5. To put that in perspective, that's about 250,000 times fainter than what the human eye can see. When astronomers calculated its orbit, they saw something remarkable. Its path was hyperbolic with an orbital eccentricity calculated to be a staggering 1.8. In astronomy, any orbit with an eccentricity greater than 1 is unbound, This number confirmed it was moving at approximately 55 kilometers per second relative to the Sun, far too fast to be a member of our solar system. Astronomers quickly named it 3I Atlas. Initial estimates suggested it could be massive, between a few hundred meters and several kilometers across, making it potentially much larger than the previous two interstellar visitors. The discovery was a major success for the Atlas network, which also includes telescopes in Hawaii and South Africa, proving its effectiveness in spotting these rare cosmic travelers. The detection of a third such object in less than a decade confirmed that these visitors are more common than previously thought, officially opening a new frontier in astronomy. Avi Loeb's controversial hypothesis. Here's where the story takes a sharp turn into speculative territory, thanks to a bold proposal from Harvard astronomer Avi Loeb. While most scientists saw a fascinating natural object, Loeb, known for his controversial work on Oumuamua, offered a different interpretation. In a scientific paper posted to the ArXiv preprint server, Loeb pointed to the object's early lack of a visible coma and its trajectory. He suggested that if the comet continued to show no outgassing, or if its path deviated from a purely gravitational path without a visible tail to explain the push, it could be evidence of something artificial. He even raised the hypothetical possibility of malign intent, though he stressed this was an intellectual exercise meant to keep science open to radical possibilities. His argument, similar to the one he made for Oumuamua, hinged on the idea that any non-gravitational acceleration without a visible coma required a novel explanation. He proposed that a solar sail, a thin, lightweight craft pushed by the pressure of sunlight itself, was one such possibility that science should not be afraid to consider, however unlikely it might seem at first. The physics of radiation pressure are well understood, but for it to be effective, an object must have a huge surface area and an extremely low mass, characteristics not found in natural bodies. Media sensation versus scientific method. You can imagine what happened next. The words alien technology from a prominent Harvard astronomer ignited a media firestorm. The idea was captivating, offering a sensational explanation for a new cosmic puzzle. But this is where the rapid world of headlines collides with the methodical, patient pace of science. The scientific method isn't about finding the most exciting answer, it's about finding the one that best fits all the evidence. The broader astronomical community, while not dismissing Loeb's right to speculate, emphasized the need for patience and adherence to Occam's razor, the principle that the simplest explanation is often the best. Their stance was clear. We must first rule out all known natural phenomena before jumping to an extraordinary conclusion. The use of preprint servers like ArXiv allows for rapid dissemination of ideas, but also bypasses the traditional peer review process, meaning speculative ideas can reach the public before they are fully vetted by other experts. Ultimately, the scientific consensus held that declaring an object alien required the elimination of every single possible natural explanation first, a very high bar that had not yet been met. NASA's comprehensive investigation. With the debate raging, NASA and its international partners marshaled their most powerful instruments. This wasn't a casual glance, it was a coordinated multi-platform investigation led by Tom Statler, NASA's lead scientist for small bodies. The agency dedicated priority time on the James Webb Space Telescope, using its near-infrared spectrograph, NIRSpec, to perform detailed chemical analysis of the gases in its coma. Simultaneously, the Hubble Space Telescope's Wide Field Camera 3 was used for high-resolution imaging to search for any faint dust or fragmentation events, thanks to its superior resolving power in visible and ultraviolet light. On the ground, a network of observatories, including the twin 10-meter mirrors of the Keck Observatory in Hawaii, began a long-term monitoring campaign to track its brightness and trajectory with pinpoint accuracy. The goal was to leave, honestly, no stone unturned, to precisely measure its path to within a few milliarc seconds, to analyze its chemical composition, and to study its light curve for clues about its shape and rotation. This multi-wavelength, multi-observatory approach is the gold standard in modern astronomy for characterizing a novel object. Comet behavior confirmed. So what did this powerful array of telescopes actually see? The answer was unambiguous, and came sooner than many expected. As 3I Atlas drew closer to the Sun, crossing the orbital distance of Jupiter at approximately 5.2 astronomical units, which is about 483 million miles, the solar radiation began to warm its icy surface. Just as predicted by standard cometary models, it started to sublimate, behaving exactly like a comet. Astronomers watched as it developed a distinct coma, the fuzzy, gaseous atmosphere around its nucleus, which grew to over 50,000 kilometers in diameter. Shortly after, a classic tale of gas and dust began to form. Tom Statler summarized the findings. It looks like a comet. It does comet things, and the evidence overwhelmingly points to it being a comet. The observation of outgassing, with a dust production rate estimated at over 50 kilograms per second, provided the natural explanation for any minor deviations in its path, rendering the artificiality hypothesis unnecessary. This behavior began right around the frost line where water ice turns to gas, a telltale sign of a natural cometary body. Chemical composition analysis. But confirming it was a comet was just the beginning. The real prize was in its chemistry. A team led by Dr. Anjali Sharma, a planetary scientist at NASA's Goddard Space Flight Center, used the James Webb Space Telescope spectrographs to break down the faint light from the coma into its chemical fingerprints. The analysis revealed familiar substances like water ice and carbon dioxide, but with a major surprise, 3I Atlas had an unusually high ratio of carbon dioxide to water, measured at nearly 35%. This vital clue suggested the comet must have formed in an extremely cold region of its home star system, far out in its protoplanetary disk, where carbon dioxide could freeze out in large quantities. Furthermore, analysis of the dust grains showed a polarization signature with negative branching at a phase angle of 22 degrees, suggesting a surface composed of very fine, porous, fluffy dust grains, which is a sign of a very pristine, unaltered body. This fluffiness implies the grains have not been heavily processed by heat or collisions, making them a near-perfect sample of their native environment. This chemical snapshot provides invaluable data for models of planetary formation in other star systems. Trajectory and safety assessment. With the "what is it" question settled, NASA also moved to definitively address any public concern about its path. The coordinated tracking campaign from both space and ground-based telescopes allowed for an extremely precise calculation of its orbit. The agency confirmed that 3I Atlas posed absolutely no threat to Earth. Its closest approach to our planet will be a very safe 1.8 astronomical units, which is about 273 million kilometers or 170 million miles away. Its perihelion, or closest approach to the Sun, is predicted for January 12, 2026, at a distance of 1.5 AU, placing it between the orbits of Earth and Mars. NASA's Planetary Defense Coordination Office used this as a perfect real-world test of their tracking systems, proving they can accurately predict the path of even novel interstellar objects with incredible precision. After it loops around the Sun, its hyperbolic trajectory will ensure it is flung back out into interstellar space, never to return. Its brief passage is a fleeting but precious scientific opportunity. Natural anomalies in cometary physics. The whole 3I Atlas controversy really boils down to a single fundamental question in science. Is an anomaly evidence of something artificial, or is it a sign of a natural process we haven't encountered before? Science almost always bets on the latter. Our own solar system is filled with comets that behave in bizarre ways. Take Comet 29P Schwassmann-Wachmann, which can increase in brightness by over 15 magnitudes, a factor of 1,000,000, in just a few hours due to cryovolcanic eruptions. Another example was Comet C 2019 Y4, or Atlas, a different comet which unexpectedly disintegrated into multiple pieces as it approached the Sun, showing how fragile these icy bodies can be. The point NASA scientists made is that unusual traits are not automatic evidence of engineering. They are part of the normal, messy, and fascinating physics of icy bodies. These anomalies are not problems for science, they are the very data points that lead to new discoveries about how objects form and evolve. Thus, the unique chemistry of 3I Atlas isn't a paradox, it's a clue. Scientific value of interstellar visitors. So if 3I Atlas is not alien technology, why is it so important? Because interstellar comets are windows into other worlds. Each one is a preserved time capsule, carrying the precise chemical and physical fingerprints of the environment where it formed. For 3I Atlas, the dominance of carbon dioxide and its trajectory suggest it could be over 7 billion years old, originating from the Milky Way's thick disk, a population of ancient stars that existed long before our Sun was born. By studying its isotopic ratios like the deuterium to hydrogen ratio in its water, scientists can get direct clues about the water in other primordial solar systems, a key factor in assessing the potential for life elsewhere. This is more than a curiosity. It is a preserved fragment of another planetary nursery. Future missions, like the ESA's Comet Interceptor, are being designed specifically to launch and wait in space, ready to chase down the next interstellar visitor for an even closer look. These objects represent a fundamental shift from studying other solar systems through the faint light of their stars to analyzing actual, physical samples. Comparing three interstellar objects. To truly appreciate 3I Atlas, you have to place it in context with its predecessors. The first, Oumuamua, discovered in 2017 with an eccentricity of 1.2, was a complete enigma. It was small, rocky-looking, showed no visible coma, yet had a mysterious acceleration. The second, 2I Borisov, found in 2019 with a high eccentricity of 3.37, was almost the opposite. Its nucleus was about 1 kilometer wide and it behaved like a classic comet, allowing for detailed study. 3I Atlas, with its eccentricity of 1.8, falls between these extremes. It behaves like a comet, which sets it apart from Oumuamua, but its distinctive chemical ratios make it stand out from a standard comet like Borisov. This growing diversity is forcing astronomers to create a new classification system for interstellar objects. The current rate of discovery suggests that at any given time, there are likely thousands of interstellar objects within our solar system, but most are too small and faint to detect. As our technology improves, we can expect to find many more of these cosmic messengers, each one adding another piece to the vast puzzle of our galaxy. In the end, Comet 3I Atlas isn't alien technology. It's a natural interstellar comet. A stunningly beautiful and scientifically priceless messenger from another star system, shedding gas and dust as it speeds through our cosmic neighborhood. The real story here isn't science fiction, but the incredible power of science itself to solve mysteries and reveal the universe's secrets. It's a rare glimpse of pristine material from another world, reminding us that the cosmos is far more diverse and fascinating than we can imagine. For more deep dives into the mysteries of our universe, don't forget to like, subscribe, and hit the bell icon. The universe always has another surprise waiting. Thank you for watching Sci and Why. On September 26, 2022, NASA achieved something truly unprecedented. They deliberately crashed a spacecraft into an asteroid at 6.6 kilometers per second and, get this, completely changed its orbit. The DART mission wasn't just about proving we could hit a space rock. No, it was humanity's first successful test of planetary defense technology. But what happened after the collision honestly shocked scientists and revealed truths about asteroids that nobody really expected. The aftermath of this cosmic collision is rewriting everything we thought we knew about protecting Earth from space threats. The journey to impact. NASA's Double Asteroid Redirection Test, or DART, began its historic journey on November 24, 2021, launching from Cape Canaveral Space Launch Complex 40 atop a SpaceX Falcon 9 rocket. The refrigerator-sized spacecraft traveled for nearly 10 months across 11 million kilometers of space to reach its target, a small asteroid moonlet called Dimorphos. The mission team, led by project scientist Dr. Nancy Chabot at the Johns Hopkins Applied Physics Laboratory, had meticulously planned every detail of this unprecedented experiment. Unlike previous space missions that aimed to study celestial objects, DART was designed with one purpose: to slam into Dimorphos and change its orbital path around the larger asteroid Didymos. The spacecraft carried advanced navigation systems that would allow it to autonomously guide itself to impact during the final 4 hours of flight, since the 11-minute communication delay with Earth made real-time control totally impossible. As DART approached its target, onboard cameras captured dramatic images of the asteroid growing larger and larger, marking humanity's first intentional collision with another world for planetary defense purposes. The perfect target. Dimorphos proved to be the ideal testing ground for this groundbreaking experiment, measuring approximately 160 meters in diameter and orbiting its larger companion Didymos every 11.9 hours. The binary asteroid system, located about 11 million kilometers from Earth at the time of impact, posed no threat to our planet, making it a safe target for this high-stakes test. Didymos, the larger asteroid measuring 780 meters across, served as the gravitational anchor for its smaller moonlet. Scientists chose this system because any change in Dimorphos's orbit could be precisely measured from Earth using ground-based telescopes and radar systems. The asteroid pair was discovered in 1996 and had been extensively studied, providing researchers with detailed baseline measurements of their orbital characteristics. The proximity of the two asteroids meant that even a small change in Dimorphos's velocity would produce a measurable shift in its orbital period around Didymos. This binary system represented the perfect natural laboratory for testing kinetic impactor technology, close enough to Earth for accurate observation, large enough to produce detectable changes, yet far enough away to ensure complete safety for our planet throughout the experiment. The moment of impact. At exactly 23:14 UTC on September 26, 2022, DART slammed into Dimorphos at a closing speed of 6.14 kilometers per second, releasing kinetic energy equivalent to approximately 2.5 tons of TNT. The collision occurred with pinpoint accuracy, striking the asteroid's surface and instantly vaporizing the 610-kilogram spacecraft along with a portion of the asteroid's rocky material. Ground-based telescopes around the world captured the dramatic moment as a brilliant flash of light erupted from the impact site, followed by an expanding cloud of debris that grew brighter over several hours. The Hubble Space Telescope and James Webb Space Telescope immediately began observing the aftermath, documenting the evolution of the ejecta plume as it stretched across thousands of kilometers of space. Within minutes of impact, the debris cloud had expanded beyond Dimorphos itself, creating a spectacular tail of material that resembled a comet's tail stretching behind the asteroid. Amateur astronomers joined professional observatories in tracking the collision's effects, witnessing history as humanity demonstrated its ability to alter the path of a celestial object. The impact created seismic waves that rippled across Dimorphos's surface, potentially reshaping the asteroid's internal structure in ways that scientists are still working to understand. Beyond all expectations. The results of the DART impact exceeded every prediction and shattered the mission's success criteria. Instead of the minimum 73-second change in orbital period that would have declared the test successful, Dimorphos's orbit around Didymos shortened by an astounding 32 minutes. This dramatic change represented a 26-fold improvement over the mission's baseline requirements, proving that kinetic impactor technology was far more effective than scientists had dared to hope. The massive orbital change resulted not just from the direct momentum transfer of the spacecraft's impact, but from the unexpected efficiency of the momentum multiplication effect created by the ejected debris. As material blasted away from the impact site, it carried additional momentum in the opposite direction, acting like a natural rocket engine that amplified the deflection effect. Dr. Tom Statler, DART program scientist at NASA, described the results as a watershed moment for planetary defense and humanity's ability to influence our cosmic environment. The orbital change was so significant that it could be measured by small telescopes and even confirmed by radar observations from Arecibo Observatory and the Goldstone Deep Space Communications Complex. This level of deflection meant that if Dimorphos had been on a collision course with Earth, the impact would have shifted its trajectory by hundreds of thousands of kilometers. The mysterious ejecta cloud. The debris cloud created by DART's impact revealed secrets about asteroid composition that puzzled scientists worldwide. Instead of the uniform dust plume that computer models predicted, the ejecta displayed complex structures including multiple debris streams, spiral patterns, and irregular particle distributions that suggested Dimorphos had a far more complex internal structure than anticipated. Dr. Christina Thomas at Northern Arizona University, who led the observational campaign, noted that the debris cloud evolved in unexpected ways over the following weeks. Some particles were ejected at speeds exceeding 500 meters per second, while others moved much more slowly, creating distinct populations of material with different trajectories and behaviors. The cloud's asymmetric shape indicated that Dimorphos wasn't a solid, uniform rock, but likely a rubble pile, a loose collection of smaller rocks and boulders held together by weak gravitational forces. High-resolution images from ground-based telescopes revealed that the ejecta contained both fine dust particles and larger chunks of material, some potentially meters in size. The debris cloud's brightness variations suggested that different types of material were being ejected from various depths within the asteroid, providing unprecedented insights into the internal layering and composition of small solar system bodies. Hera's investigative mission. Recognizing the need to understand DART's impact in detail, the European Space Agency launched the Hera mission in October 2024 to conduct a comprehensive post-impact investigation. This follow-up mission represents an unprecedented example of international cooperation in planetary defense, with Hera scheduled to arrive at the Didymos system in late 2026 to examine the crater left by DART's collision. The spacecraft carries advanced instruments including high-resolution cameras, thermal imagers, and radar subsystems designed to map both asteroids down to centimeter-scale resolution. Hera will measure the precise size and depth of DART's impact crater, analyze the composition of exposed subsurface material, and determine how the impact altered the internal structure of both Dimorphos and its parent asteroid Didymos. The mission will also deploy two small CubeSats called Juventus and Milani to conduct complementary investigations, including the first radar sounding of an asteroid's interior and detailed gravitational field mapping. Dr. Patrick Michel, Hera's principal investigator, emphasized that understanding the physical properties revealed by DART's impact is crucial for designing future deflection missions. The data collected by Hera will validate computer models used to predict deflection effectiveness and provide the foundation for operational planetary defense systems. Unraveling asteroid mysteries. The DART impact revealed that small asteroids like Dimorphos are far more complex than scientists previously understood, fundamentally changing how we think about these cosmic building blocks. Pre-impact models assumed asteroids were relatively simple objects with predictable responses to external forces, but the dramatic success of the deflection demonstrated that rubble pile asteroids behave more like fluid structures than solid rocks. Dr. Andy Rivkin at the Johns Hopkins Applied Physics Laboratory noted that the impact's efficiency suggested Dimorphos has very low internal cohesion, allowing the impact energy to propagate throughout the entire structure and eject material from multiple locations. The asteroid's surface appears to be covered in loose regolith, fine, rocky debris accumulated over millions of years, that was easily disturbed by the impact's shock waves. Spectroscopic observations of the ejecta revealed that Dimorphos contains ordinary chondrite minerals, similar to the most common meteorites found on Earth, but with unusual proportions that suggest a complex formation history. The impact also provided insights into how small asteroids respond to tidal forces from their parent bodies, with evidence suggesting that Dimorphos experiences ongoing surface changes due to its proximity to Didymos. These discoveries have profound implications for understanding asteroid evolution, the formation of binary systems, and the potential resources available on near-Earth asteroids for future space missions. Complications for future defense. While DART proved that kinetic impactors can deflect asteroids, the mission also revealed complications that will influence future planetary defense strategies. The unexpectedly large orbital change, while impressive, highlighted just how difficult it is to predict exactly how different asteroids will respond to impact. Dr. Nancy Chabot emphasized that the momentum multiplication factor, the ratio of total momentum change to the spacecraft's initial momentum, varied significantly from pre-impact predictions, reaching values between 2.2 and 4.9 depending on the measurement method. This variability means that future deflection missions will require detailed advanced characterization of target asteroids to predict their response accurately. The complex ejecta pattern suggested that asteroid internal structure, surface composition, and rotation state all influence deflection efficiency in ways that current models just don't fully capture. The discovery that small asteroids behave more like loosely bound rubble piles than solid objects means that deflection strategies must account for potentially dramatic differences in material properties between different asteroid types. Mission planners now recognize that successful planetary defense will require a library of deflection techniques tailored to specific asteroid characteristics, rather than a one-size-fits-all approach. The DART results also emphasize the importance of early detection and characterization, since deflection effectiveness depends critically on understanding an asteroid's physical properties years before any potential impact threat. Global Planetary Defense Initiative. The success of the DART mission has catalyzed unprecedented international cooperation in planetary defense, transforming what was once considered science fiction into practical space policy. NASA's Planetary Defense Coordination Office, established in 2016, now works closely with the European Space Agency, Japan's JAXA, and other international partners to develop comprehensive strategies for detecting and deflecting hazardous near-Earth objects. The United Nations Office for Outer Space Affairs has established new protocols for sharing asteroid tracking data and coordinating deflection missions, recognizing that planetary defense is a global responsibility requiring multinational collaboration. Ground-based survey telescopes like the Catalina Sky Survey in Arizona and the Linear program in New Mexico continue discovering new potentially hazardous asteroids at rates exceeding 1,000 per year, building a comprehensive catalog of objects that might someday threaten Earth. Space-based detection systems, including NASA's NEOWISE mission and the planned NEO Surveyor telescope, will dramatically improve our ability to find and track smaller asteroids that ground-based systems might miss. The establishment of the International Asteroid Warning Network ensures that discovery data reaches decision-makers quickly enough to enable deflection missions if needed. These coordinated efforts represent humanity's first serious attempt to protect our planet from cosmic threats that have caused mass extinctions throughout Earth's history. The future of planetary defense. The DART mission's spectacular success has laid the foundation for humanity's first operational planetary defense system, but it also revealed how much we still need to learn about deflecting dangerous asteroids. Future missions will build on DART's legacy by testing different deflection techniques including gravity tractors, nuclear standoff detonations, and enhanced kinetic impactors designed for specific asteroid types and threat scenarios. NASA's follow-up missions are already in development, including concepts for multi-spacecraft deflection systems that could handle larger asteroids or provide backup capabilities for critical deflection attempts. The double asteroid redirection test proved that humanity possesses the technological capability to alter the course of celestial objects, marking our species' transition from passive observers of cosmic events to active participants in shaping our solar system's dynamics. Advanced computer simulations now incorporate DART's impact data to model deflection scenarios with unprecedented accuracy, enabling mission planners to design precise interventions for specific threat asteroids. The mission's success has also sparked development of rapid response deflection technologies that could be deployed on shorter timescales for newly discovered threats. Most importantly, DART demonstrated that international cooperation and scientific expertise can overcome seemingly impossible challenges, providing a template for tackling other global threats that require coordinated human action on planetary scales. So there you have it. NASA didn't just hit an asteroid, they revolutionized planetary defense and revealed that asteroids are far stranger than we imagined. Which discovery about the DART mission surprised you the most? Let me know in the comments below. If you enjoyed learning about humanity's first successful planetary defense test, make sure to like this video, share it with someone who loves real space breakthroughs, and don't forget to subscribe to Sci and Y for more incredible discoveries about our universe. Until next time, keep exploring the cosmos.